Hello, everyone, and welcome to AP Chemistry Section 1.7, which is all about periodic trends or periodicity. In it, we're going to be looking at some patterns that the elements display as we move around the periodic table. Patterns like in atomic radius, ionization energy, electron affinity, and electronegativity. And we'll look at how best to explain what's going on if we're ever asked questions about it. And stay tuned for the end of the video. I'll throw in a couple of pointers about how to write your free responses if you see questions like this on your AP exam. So hope you're ready to go. Grab your periodic table and let's get started. Turns out the elements, as they're arranged on the periodic table, make a bunch of really cool patterns. For starters, let's talk about metals versus nonmetals. You might know that these elements over here on the left-hand side of the periodic table are metals, like the alkaline metals and the alkaline earth metals. And then we have the transition metals, and then we get into this section over here where we get the metalloids and the nonmetals. So typically, as you go from left to right, you're getting more non-metallic or less metallic along the way. So those are a general pattern right there. But periodicity is all about recognizing and identifying and explaining patterns in atomic properties. If you've never done this before, let's just take a moment and make an observation or two. So here is a chart. There's millions of them out there, and you can find them. And it shows relative sizes of atoms, commonly given as atomic radius. And the atomic radius is calculated as basically half the distance between two nuclei in a bond with itself. And so we get these numbers. Now, you don't have to memorize the numbers. That would be a lot unless you just really want to. But you'd be presented with data like this. But take a look. Can you see the patterns like right off the bat? You might notice, first of all, that these down here are really large comparatively, and these up here are pretty small, hydrogen being the tiniest. Now, periodic observations are generally made going across a period or down a group. So as we look down the group here, I can see the atoms are getting bigger. And as I go across from left to right, they are getting smaller. And that's kind of the tough one right there, because you might think that beryllium, having one more proton and one more electron, has more stuff in it, probably more neutrons too. You would think that it would be bigger because there's more subatomic particles in that atom. But as you keep adding things to it, the atoms get a little bit smaller. So we have to explain why. Okay, so let's take a look at just another quick representation of it. This type of data can be presented in all kinds of different ways that you might see. Here is just a bar graph showing, and it's upside down too. So we've got row 4 moving across, row 5 is up here, and row 6. Again, potassium, rubidium, and cesium, here's that big atom, and then they generally get smaller. Now, it's not a perfect trend. Periodic trends are not hard and fast. They're kind of general things, and there are exceptions to them, so we have to be careful with those. But that's another way to look at it. So how can we explain what is going on here? Why are they getting bigger as you go down, but smaller as you go across? Well, let's do the first one first. That's the easier one. These are getting bigger because each row of the periodic table adds an energy level. So 1s, 2s, 3s, 4s, 5s, 6s. So we're basically moving outward from the nucleus, and it might make sense that the atoms get bigger. So, but that being said, why do they get smaller? So you may want to pause the video if you need to write this down. Atomic radius increases as you go down a group because the added energy levels expand the atom outward. And also, there's something called core shielding. The lower electrons sort of block the view of the nucleus or the pull from the nucleus because those outer electrons are actually repelled by the middle electrons or the lower electrons. So there's a little bit of shielding going on there. So the outer electrons can kind of stray a little bit farther from the nucleus. But atomic radius decreases across the period because, yes, you're adding more electrons as you go across, but you're also adding more protons, so more nuclear charge. And what that does is it pulls the same set of energy levels closer. So as we move across a row, we're not really adding big energy levels to it. We're just adding protons to what's there, and it pulls the electrons in a little bit closer. Okay, so we'll need to be able to know how to explain that. And in general, this is the general trend in atomic radii. So increases left and down. All right, let's do ionization energy next. Ionization energy is the energy required to remove an electron from the outermost orbital of an atom. This is the first ionization energy. Okay, and take a moment to write that down if you need that. Here is a graph of ionization energies. Okay, and they're usually given in kilojoules per mole. So if you had a mole of those atoms and you ripped out electrons from all 6.02 times 10 to the 23rd of them, how many kilojoules would it take? So notice hydrogen, helium, those are really tall. The next row gets a little bit lower, but generally increases as you go left to right. And here we have a little bit less, but generally increasing, and a little bit less, but generally increasing as well. So ionization energy typically decreases as you go down a group, and increases across a period. So it's exactly the opposite of atomic radius. I always tell my students, if you can remember the trend for atomic radius, bigger left and down, all the other trends are bigger up and to the right. And here's another version of that. You can see that starting with, for example, the noble gases, as you go down the group of the noble gases, each one gets a little bit less and less and less. But after each noble gas, you get a really big drop to an alkaline metal, and then a slow increase up until you get to the next noble gas, and then off the cliff again. Here we go. And so it's again, it's not a perfect pattern, but it is a definite pattern in those ionization energies. So why does this happen? So ionization energy decreases down a group because the atoms get bigger down the group, right? Those outer electrons are farther from the nucleus, the bigger the atomic radius is, so they're more easily removed with less energy. So that's part A. And it increases across a period kind of for the same reason that the atoms get smaller across the period. The energy levels are held closer to the nucleus by that effective nuclear charge, those extra protons, and are also more full, a little more stable too. So, but mostly it's the effective nuclear charge. So the same reason why some atoms are big gives them low ionization energies. And the same reason why some atoms are small gives you big ionization energies. So the hydrogen and helium, being the tiniest atoms, have a lot of energy needed to take those electrons away. And so here's our general trend on that. Now, I should also note that there is not only first ionization energies, but second and third and fourth, and all of that. And that's because you sometimes don't just remove one electron. You want to remove a second one and a third one. And those first ionization energies are written here in this first column. Notice that the second ones are always bigger than the first ones. All right, and that's because once you lose an electron, the remaining electrons are going to be held tighter to the nucleus because now the protons are ganging up on the electrons that remain, and they get a little closer. The atom gets a little smaller. Cations are always smaller than their neutral atoms. And then it's harder to remove that second electron, and then harder to remove the third and fourth, and so on. Now, you'll probably see questions about the big jumps. Like, you can tell how many valence electrons an atom has by how easily it loses electrons down the line. So for example, let's look at lithium for a moment. Lithium, it's pretty easy, a low number to remove the first electron, but it's really high. It's like 12, 15 times as high. There's a big jump right there. Okay? Because it only has one valence electron, because once that valence electron comes out, the second one has to be taken from one of the core electrons, and that's in a full energy level, and that's harder to take. Beryllium has two valence electrons, 1s2, 2s2. And so the first one is kind of low, the second one's kind of low, but after that second one, look at that big jump from 1700 to 14,800. And that's a big jump. And so that indicates that those are two core valence electrons, and the rest are core electrons. Boron has three valence electrons, so the big jump occurs after number 3, and so on down the line. You'll often see charts like this with a zigzaggy line separating the valence electrons from the core electrons. And then the pattern repeats once you get over to sodium. Starts low, next one's really high. Magnesium has 2 that are kind of low, aluminum has 3 that are kind of low, and so on. So you kind of don't memorize the numbers. That's a lot of numbers to remember. But look for the big jumps and how many electrons it takes you to get there, because that helps you identify how many valence electrons it has and sometimes what element it actually is. Okay, let's do electron affinity. Electron affinity is kind of the opposite of ionization energy in terms of its definition. Energy is required to be added to remove electrons from an atom because they have to move up the energy levels and then out of the atom. But if electrons go in, energy is released. And it's a very similar amount of energy, and we call that electron affinity. Again, it's given in kilojoules per mole. And it might make sense that it's going up as you go to the right because atoms are getting smaller. The more energy it takes, the higher ionization energy it takes to remove an electron, the more you get it when it comes back. And so that's why the trend in ionization energy and electron affinity, let's look at them again, are fairly similar in their trend. So that's electron affinity. And there's our overall pattern. It should be noted that cations are always smaller than their neutral atoms. So this is a chart showing generally what the size would have been, but what they are now as ions. Lithium gets smaller. It was 152, but now it's 78. Beryllium, 113, and now it's 34. And in general, the higher the charge, the positive charge, the tinier the atom gets. You're losing more and more electrons, and those remaining protons just gang up on the remaining electrons and make it really small. So the higher the charge, generally the smaller the cation. On the other hand, these guys over here, when they gain electrons to become anions, they get bigger. And that might make sense too, because you're adding electrons, and those electrons repel each other and can kind of stray a little bit farther from the nucleus because now there's only a minimum number of protons in the nucleus, and now you've added electrons, so they get to run around a little bit freer and make the atom a little bit larger. Again, the more negative the charge is, generally the bigger the anion is going to be in terms of its size. Let's talk about electronegativity for a moment. Electronegativity is generally the ability of an element to attract electrons unto themselves in a chemical bond. So we're going to talk about chemical bonding next unit. And one of the main themes is that when atoms share electrons, they don't often share them equally. Maybe one is attracting the electrons more than the other one is. And electronegativity is a measure of that. It's given on a 4.0 scale, developed by a guy who got a really great name, Linus Pauling. It's one of the best chemical names out there. And electronegativity increases up and to the right, kind of like ionization energy. Again, you don't have to memorize these numbers. If you ever need them, you'd be provided with them. But in general, the smallest values are down here, and the largest values are up here. So fluorine is the king of electronegativity, followed by oxygen, chlorine, nitrogen, and these guys up here in the corner. All right, and we'll do one quick summary, and then we'll start looking at some questions. So you might see a chart like this. Take a moment, just jot it down, or Google it. You'll probably find a million of them on Google as well. And now let's take a look at some questions, typical of what you might see on an AP exam, starting with an easier one and moving toward some harder ones. Let's start with this one. Which pair of elements is expected to have the most similar properties? By now you may know that things that are in the same column of the periodic table tend to have similar properties, like the alkali metals, the alkaline earth metals, the noble gases, and so on. So we're looking first for things that are in the same column, and right off the bat I see potassium and lithium, which are both in the first column of the periodic table over there. I would expect them to have similar chemical and physical properties. All right, the atom with the largest radius is, and they give us 4 choices: krypton, strontium, uranium, and bromine. So you might have to go find them. Krypton, bromine, strontium, and uranium is down here. So you'll always have a periodic table. Just know how to use it and know which way the trends go. And I'm looking for something that's either farthest left or farthest down. And I see that strontium is way over here on the left. Now you might think that uranium would be the biggest one because it's farther down, but in fact these elements right here actually slide in this little spot. So uranium is actually to the right of strontium. And so strontium is going to be my choice for the largest radius. The next one is also an atomic radius question, but we'll do a pause the video moment and see if you can find which pair of elements is the larger atom listed first. So take a moment, pause the video. I'll see you back here in a minute. And if you chose A right off the bat, then perfect, because potassium is just to the left of calcium. Calcium is farther to the right. Calcium has one more proton than potassium does, so it pulls its energy levels in a little bit smaller, a little closer, and we can double check that. There's potassium, there's calcium. All right. Next one is about the explanation for that. Atomic size increases going from top to bottom in a group because the number of protons increases, the number of electron shells increases, the atomic mass increases, or the atomic volume increases. All right, atomic size does increase, which does increase the atomic volume, but it's not the reason why it happens. It's because of the number of those electron shells actually increases. Okay. The next couple are fairly similarly worded, so we'll try one together and then I'll have you pause the video. The first ionization energy of sodium is 496 and its atomic radius is 186. Based on this information and your knowledge of the periodic trends, which values are the most reasonable for the radius and first ionization of the magnesium atom? Okay, you might have to go and find them again. So here we're given information about sodium. Magnesium is right next door. So we want to know what's some reasonable estimates for magnesium. Now, because magnesium has one more proton, we would expect it to be a little bit smaller. So let's first look for something that has a smaller radius than 186, and that gives me the first two. Okay. Then I also have to decide which combination of ionization energies is most favorable. Now, because magnesium is smaller in radius, we would expect a higher ionization energy because it's going to the right. So I'm going to go with A, 160 and 737, which is higher than the 496 that we see there. And that's the thought process you might use. All right, let's do another one. Carbon has an atomic radius of 77 and a first ionization energy of 1086. Based on your periodic trends and the data given above, what are the most probable values for the ionization energy and atomic radius of nitrogen? Take a moment, pause the video. I'll see you back here in a couple of seconds. All right, we are looking for something that is a little bit smaller than 77. That gives us A and D as our choices. And something with a higher ionization energy because it has one more proton. So again, we're looking at letter A on that one. And our last multiple choice question for this episode is this one. Of the following, the species that has the largest radius is? Now, they've given us 4, but they're ions, and that's a little added level of complexity there. So we got chloride ion, bromide ion, potassium, and strontium ions. Okay, so how do we break this down? Especially if I haven't memorized all the ionic radii, because that's just a lot of information. Well, first, I'm going to look for the one with the largest radius. So that steers me toward the anions, because remember, anions get bigger when they gain those electrons. So they expand a little bit further outwards. So they're going to get bigger while the cations are going to get smaller. So I'm just going to avoid the 2 cations in this list because they are getting smaller, and I can already see from a chart like this that they would be smaller. So we're going to ignore the cations, but then I have to worry about chlorine and bromine. Now they're both 1- ions. They've gained 1 electron each, and so they both expand a little bit. So which one ends up bigger? The one that started out bigger, and that would be the bromine. Bromine is 1 row down from chlorine on the periodic table. It's got another energy level. So it already starts out bigger, and you add an electron to both of them. They both expand, but bromine ends up bigger because it started out bigger. And that's how we would attack that one. Let's look at a couple of prompts that you might see in a free response question. These are fairly typical types of questions dealing with periodicity. And it'll say something like this: using principles of atomic structure or maybe chemical bonding or something like that, explain the following. And it'll tell us potassium atoms have a larger radius than copper atoms. So in this case, we don't actually have to predict which is bigger. We are told that it's bigger. We are supposed to justify that and say why it's bigger. And the first ionization energy of iodine is less than the first ionization energy of chlorine. And again, they just tell us that. We're supposed to justify that with some complete sentences and a thoughtful response. So you might be wondering, how should I write my response to a question like this? Because I want to get full credit on it and do well on my AP chemistry exam. I want to hit you with a couple of quick hints on something like this to avoid. First, when you're asked a free response question like this, when you're asked to compare two elements or ions, you must discuss both in your answer. So don't just say with respect to one, like potassium is bigger because it has blah, blah, blah. You want to make sure you mention both of the atoms or ions in them. Also, and this is a big one, do not use their positions on the periodic table as a justification. So we're told potassium is bigger than copper, right? Potassium is there, copper would be somewhere here in the middle. It's tempting to write something like potassium is bigger than copper because it's farther left on the periodic table, or because copper is farther right on the periodic table. That may be true, but it is not a justification, and you won't get credit for an answer like that. You have to talk instead about electronic structures, nuclear charge, the ion charge, et cetera, et cetera, et cetera. So don't use its position to justify anything. It happens to be left of copper on the periodic table, but that doesn't explain why it's bigger. So I'll show you a couple of responses that I came up with for these two. I said for the first one, potassium atoms have a larger radius than copper atoms. I basically restated the question so that the person reading my answer knows that I'm going for the prompt. I'm answering the right prompt. And then I said, because even though copper atoms have more electrons, I threw that in there so that my grader would actually have a better idea that I know what I'm talking about. Yes, I understand they have more electrons, but the copper atoms also have more protons. This larger nuclear charge causes the electron shells to be pulled closer to the nucleus, resulting in a smaller radius than potassium, which has fewer protons in the nucleus. So again, I've mentioned both. I've talked about the atomic structure. I did not say one is farther left or farther right. That would not get me full credit on that answer. Hopefully that makes sense. Jot those down as hints so you can do well on your own exams. The first ionization energy of iodine is less than the first ionization energy of chlorine. Again, I restated it because iodine's outer electrons exist in the 5p orbital, while chlorine's outer electrons are in the 3p orbitals. The 5p orbitals are farther away from the nucleus, resulting in less energy needed to remove them, while chlorine's 3p electrons require more energy to be removed because they are closer to the nucleus. So again, mention both. Don't use their positions to justify their periodicity. Okay, so I hope you found that helpful. We did a lot in this episode, and if you have any questions or comments, send them to me in the comment section. And in the meantime, happy studying and have a great day.